We got this situation where I have, well, let's just read the situation. Find the acceleration of a sled pulled by a mother. Okay, that seems like a nice little story. Sled pulled by a mother. So here's our sled. Here's a mother. She's pulling up on the sled as she slides it across. There's a child on the sled. Okay. And it says the combined mass of the child. Oh, that doesn't look like a child. Let's give it a head. There's a child on the sled, and somehow, you want arms and legs? Okay, whatever. So you don't have to be an artist. We got a child on a sled here. Mother's pulling along. The combined mass of the sled and the child is 50 kilograms, and the mother pulls with a force of 600 newtons at an angle 30 degrees above the horizontal, and the friction between the sled is 40 newtons. And so we got this picture here. We're going to add on to it. So mother's going to pull with what we say she can pull with, 600 newtons. Let's call that the F applied. It says that she pulls at an angle 30 degrees above the horizontal, so 30.0 degrees. We've got an FG pulling down on this sled. That makes sense. And it seems to me that if there's a friction force, doesn't that kind of leave this last force as the friction force? Must be, right? So we've got an FK equaling 40.0 newtons. All right, good so far. What can we figure out? Oh, you know what? If we apply a force upwards, it's going to have an X component and a Y component. So we're going to have a FAP-X, and we're going to have a FAP-E. Now, as I look at this, if I wanted to come up with an equation for FAP-E, FAP-E is going to have the equation, look, isn't FAP-E the opposite? So we're going to have FAP-E is equal to FAP times sine theta or cosine theta if it's opposite. Sine theta. FAP-X is going to be F applied times cosine theta. Great. I only bring that up because we're going to have to think about X and Y components. One thing that we haven't included in our diagram is an upwards force. What would you call the force that keeps the kid in the sled from falling through the snow? Starts with an N. Normal. If I pull upwards, would the force due to gravity and the force normal be equal to each other, or would one of them be bigger and one be smaller? Think about it. I got an eraser here. If I pull ever so slightly up on this eraser, not hard enough to make it leave the ground, but just ever so slightly up, am I making the desk work harder or less hard? Less hard, right? So if I pull up on this thing, yeah, there's going to be a normal force, but let's agree that the normal force would be diminished. It wouldn't be the same as force due to gravity. In fact, what we could say, couldn't we say that the normal force plus F applied Y would have to cancel out the FG if this kid doesn't leave the ground? What we're really saying is that the net force in the Y direction is 0. And that's going to be something that's always true for things that slide horizontally across surfaces. So let's actually deal with that first, okay? F net Y, being a Y thinker right now, for anything that's sliding across a surface, even if there's an applied force, F net Y, in this case, would be F normal plus Fg plus F applied Y, the Y component of the applied force. But if you're sliding something across the surface of a table, in the special case, maybe I'll even put this in writing. We'll say that it's 0 if the sled doesn't go flying. And I could even say if the sled doesn't go flying or crash through the earth, because that's even less likely, right? And if you've ever seen kids on sleds, I have never seen a kid crash through the surface of the earth, and I can't imagine a mother throwing their child on a sled, Okay, maybe, I don't know, maybe it seems more like something my father would have done, honestly, like just for thrills. But we're not throwing our children on sleds, okay? And so what that means is that F net y is going to be equal to 0 so long as the sled slides horizontally along the surface. That being the case, if I wanted to find the normal force, I could say, hey, take everything over to the other side. And I would say F normal is equal to negative Fg, negative F applied y. Okay? I want to come back to this, because I'd like to figure out what the normal force is later, just as like a thought, that I need to think out to completion. But we do have a normal force formula now. We got F normal is equal to negative Fg minus F applied y. I don't know the F applied y value yet, though, so I want to come back to it. So I'm going to just put this off in a little box for myself, and I'll come back to it later. Right now, though, I want to be an x and y thinker again. I want to say, okay, well, in the x direction, I've got a kinetic friction force that's equal to 40 newtons. And as I write this friction force, I think, well, should it be positive or negative? And I realize, what have I forgotten to do? A reference frame. That's basic. Yeah. Only noobs miss this. Up, down, right, left. Positive, negative, positive, negative. Okay. So having said that, is FK positive or negative? Negative. I'm going to draw attention to it with a red pen. Like I said, if you've bought a clicky pen or something, it's nice to draw attention to this now, like in notes, because later on when you do your homework, you're like, oh yeah, that's why that's negative. Okay, so it's a little bit of a help for you too, right? I'm probably like narrating too much, but still, I would like you to try and get in the practice of being thoughtful about your note taking so that when you go to solve problems, you have some sort of a thing to fall back on. Anyway, this F applied x, we already said, is going to be F applied times cosine of theta. And we can plug in our values. The F applied by mom was 600 newtons times cosine of 30 degrees. Again, somebody pointed out that cosine of 30 degrees is kind of a special angle because it's the square root of an integer, but I still can't do it in my head. So what's 600 cos 30? Yeah, 519.6. I feel like there's more. 6.1. 6.15242. I'll stop at the 5. That's good. Okay, newtons. And then if I'm being a y thinker, I'm not going to get to my F net stage of things just yet. If I'm being a y thinker, I'm going to say, okay, well, in the y direction, I could say that, well, didn't we already declare that F net in the y direction is going to be equal to 0 newtons? Because the kid isn't flying into the air and the kid isn't crashing through the earth. So if I want to find the net force on this person, which I'm going to have to do to find their acceleration, y isn't going to come into the story. Like I said, I do want to backtrack later to see if we can figure out what the normal force is going to be. But as of right now, can you see that the y isn't going to contribute to their acceleration? Okay, so I want to just like leave that as it is. Because we've got Fg equals mass times acceleration due to gravity, which would be our 10 kilograms. No, not 10 kilograms, 50 kilograms times 9.81 meters per second squared. And that would give us 400 and, no, that's not right. 50 times 90? Oh, yeah, 490.5. 490.5 newtons. That would be our force due to gravity. Our F applied y, going to be, we said it before, F applied times sine of 30, 600 newtons times sine of 30. Sine of 30 degrees is a magic number. It's 1/2. Sine 30 is 0.5. Yep. Oh, you're right. Yeah, we could say that it's negative for sure. Thank you. Force due to gravity is negative. F applied by mom is positive. And sine 30 is a half. Half of 600 is 300. So 300 newtons. But we're saying that this plus the F normal, which we don't know yet, those guys are all going to add up to 0 for kids that don't fly into the air. Okay? And so what's going to contribute to the kid's acceleration is all the x information. So we can say, okay, well, F net x, let's put it underneath the x column, F net x is equal to Fk plus F applied x. Fk is negative 40 newtons. We said that before. F applied x is 519.615 newtons. Notice that negative 40 means it's working against mom. And maybe you can do this in your head. What do you get? It's in the high 400s.
479.6.
Yeah, 479.615 newtons. I'm going to leave the unrounded, right? Don't round it off prematurely. I know some of you guys did that on your last test, a little premature rounding. Burns you just a little bit. Well, introduces error. And so if I want to find the acceleration, it's F net divided by mass. Remember that net is important. All the net force is coming from the x this time. So 479.615 newtons divided by the Sled Kid combo, 50 kilograms. Gives us an acceleration of, my notes, you guys correct me if I'm wrong, my notes say 9.5923 meters per second squared. Yeah? You got nods of the head. And I'm going to round this off to, what did I have? 3 significant figures, 9.59 meters per second squared to the right. And there we could have a therefore statement. Therefore, the sled and child, not child, oh my gosh. What happened to my spell check there? It just turned into like a cello or something. Child, accelerate at 9.59 meters per second squared. Right. Now that's the answer to the question. But I wanted to figure out what the normal force is. Now, I'm going to be really transparent about this. The reason I want to find out what the normal force is that later on, like in the next step of our learning, we're going to be talking about why that normal force matters and how it actually impacts friction. Okay, so this time I spoon-fed you a friction value, but later on we're going to need to know how to calculate the normal force so we can figure out some stuff to do with actual friction calculations. Okay, so I want to do this backtracking not just because I'm curious, but because I want to show how to do it, okay, so that we have it in our back pocket. Really am a big believer in having seen something once and then coming back and revisiting it again. Okay, so let's just see how we deal with this. I want to zoom back up to this normal force calculation and say, okay, well, we had some logic for why normal force was going to be calculated like this. Negative of Fg, so I've got a negative sign from the formula, and we had it pointed out to us that it's negative of, and I'll highlight that this negative sign is from the reference frame, negative of negative 490.5 newtons minus F applied y, which was 300 newtons, but minus a positive value, 300 newtons. And so we end up having positive 490.5, because negative of a negative is a positive. Positive 490.5 minus 300 gives us 190.5 newtons as the normal force. Something I want to notice about this, and yes, this would be useful later on for when we do things like calculate friction, but I want to draw attention to our free body diagram. Can you guys see that the normal force is 190.5 newtons, which is definitely less than what gravity was? We've reduced the normal force. We've taken the pressure off, if you like. And if you're somebody who ever moves furniture and you want to move a couch, it actually turns out that even though like mechanically with your body, it's easier to lean on the couch to slide it, you actually have to apply less force if you lift on the couch on an angle to slide it, because what you're doing is you're reducing the normal force. That is the contact force between the couch and the floor. And by reducing the normal force, you're actually reducing friction. So you actually have less friction to work against if you lift up on the couch slightly while you slide it. Can you guys picture mechanically like what I'm talking about there? You can do the same thing with the kitchen chair, or I don't know, don't move around your parents' kitchen table too much or whatever. But like moving appliances. Anytime I've moved my family members, my brother-in-law, my sister, whatever, I don't like go through a physics lesson with them. But I say, when we move the couch, could we lift a little bit while we slide? Because it actually is easier, right? And so this is sort of the proof as to why it would be easier. Later on, by the way, we're going to introduce something called the coefficient of friction. And when we talk about kinetic friction, there's going to be a coefficient called the coefficient of kinetic friction. And I'm just going to throw out this one little equation right now. We won't even do any calculations with it. I just want it to sort of percolate and steep like a good bag of tea for a bit on your brain. If I reduce this normal force, no matter what that coefficient is, by the way, the coefficient is just like a numerical multiplier. No matter what that number is, if I reduce the normal force, can you see that it would reduce the friction force? So for right now, it's just a formula, but I'm putting it out there that when we reduce the normal force, we reduce the friction, okay? And that should be something that bears itself out in our free body diagrams, and it should give us evidence in our calculations. Cool? Or you can just move a couch and try it out for yourself, because it's going to work out.